Good day! With this visual lesson, we're going to discuss the topic Central Limit Theorem under your probability and statistics. Our lesson objectives: at the end of this lesson, you are expected to illustrate the Central Limit Theorem and defines the sampling distribution of the sample mean using the Central Limit Theorem. Abraham de Moivre. The man on the picture below is the first person to prove the central limit theorem. He is Abraham de Moivre, a French Huguenot refugee in London. So this is the picture of Abraham de Moivre, a French Huguenot refugee in London and considered as the first person to prove the central limit theorem. Definition of term or central limit theorem. The central limit theorem states that as sample size becomes larger, the sampling distribution of the sample means approaches to normal distribution, regardless of that variable's distribution in the population. What we need to take note about your central limit theorem is that even your sample size becomes larger and larger and larger, still your sampling distribution of the sample means approaches the normal distribution. So meaning to say, regardless of how large your sample size to be subjected, still your sampling distribution of the sample means approaches the normal distribution. This fact holds especially true for sample sizes is greater or equal to 30. So we simply apply your central limit theorem if your sample size is greater than or equal to 30. So that's how we apply your central limit theorem. The more samples you have, the more it will likely to be a normal distribution. Yes, it is because it makes your distribution more reliable and you can have your valid conclusion. So when your sample size increases, it makes your conclusion more reliable and valid because it represents your population. This theorem can be applied automatically to sampling from infinite population. So we apply this central limit theorem to a large population when we are dealing with when we are dealing with a large population. In statistics, central limit theorem justifies the use of the methods of normal curve for a wide range of problems. Again, what we need to take note about your central limit theorem is that even your sample size becomes larger and larger and larger, still the sampling distribution of the sample means approaches to your normal distribution. So the histogram from this slide are the results of sample tests, which is rolling a die. So we use the experiment rolling a die. We notice that the more times you roll a die or the sample size, the more likely the shape of the distribution of the means approaches the normal distribution. So because the number of possible outcomes will be dependent on how many times we're going to roll a die. Then, to further understand the concept of the central limit theorem, let us consider a population consists of 1 with your first figure, and in your second figure which is 2, then in your third figure which is 3, So there's an involvement of your sample size, which is equal to 1, 2, 3, 4 in your fourth figure and 5 to your fifth figure. Now, the sample size of 2, 3, and 4 are drawn from this population. So we're going to use these 2, 3, and 4 for us to compare. No. Now, let us observe and compare the mean, variance, and standard deviation of the population and the sampling distribution of the means. So let's try to observe the following uh, values that we can see in your table. So the following are observations, no, in the sampling distribution. So first thing that we can observe in this one, that the sample mean mu x in your first, when your n or when your population is equal to 5 and your sample size is equal to 2, your sample mean mu x is always the same even if you increase the sample size. So if you try to look at this one, no, your sample mean is always the same even if you increase the sample size. No, even when your sample size increases from 2, 3 up to 4, still your sample mean here, which is your mu x, is still the same. So as you observe, no, even your n or your sample size increases, your sample mean is still the same. Next, the population mean mu. So dealing with this population mean mu here, no? So if you try to look at this table, there's values of your mu or your population mean is always equal to the mean of the sampling distribution of the sample means mu x, even if the sample size increase. No, even the sample size increase or there's an increase in your sample size, still your population mean mu is equal to your sample mean mu x. No, even if you started from your 2 as your sample size up to 4 as your value of your sample size, then your sample mean will be equal, no, still will be equal to your population mean. That's why your mu x is equal to your mu, or simply your sample mean is equal to your population mean. The next thing to observe, no, the variance q or the variance sigma square x. So this one, so we're dealing with this sigma square x, no, and the standard deviation of sampling distribution of the mean increases when the sample size is smaller. So as you can see, no, the values of your variance and standard deviation, if your n is 2, is bigger or more than, no, to the values of your variance compared to your if your n is equal to 3. Meaning to say, if your n or your sample size increases, then the value of your variance and standard deviation decreases. Because if n or the sample size increases, it will lessen the errors or differences or the gap between your data. That those data to be subjected, no, in your research. Now, if your n is smaller, then there is a bigger value of your variance and standard deviation. So what we need to take note of this one, no, if your n increases, then the value of your variance and your standard deviation decreases. But if your n gets smaller and smaller, then your variance and standard deviation, or the values of these two, uh, gets or increases. No. Definition of terms. So let's deal with the definition of your variance and standard deviation and finite and infinite population. So the variance and standard deviation. So it tells us how far each number in the set is from the mean. When there is a wider range of numbers in the group, the variance is greater. So you need to take note of that. When there is a wider range of numbers in the group, the variance is greater. And when there is a narrower range of number in the group, the lesser the variance. Because your variance represents the percent of errors. Meaning to say, if there is a wider range of numbers in the group, then there's a bigger graph or a bigger gap, no, between your data. So there is a bigger value of your variance. So when there is a narrower, meaning to say your data or datas are not scattered, then there is a less, or the value or the error that we're going to encounter with this one is being lessened. That's why if there is a narrower range of number in the group, the lesser the variance, because your variance will represent the percent of error. If there is, if your data is not scattered, then are not scattered, I mean, then there is a minimal error, or there is a minimal differences or gap between your data. That's why there is a lesser value of a variance. Now, dealing with this finite and infinite population, dealing with your infinite population, it refers contains infinitely elements, while finite population consists a fixed or finite number of elements. When you say when you're dealing with your infinite population, there is a fixed value of numbers of elements that you're going to subject in your research. So in your infinite, so it can be from up to the last drop, no? So infinity. So you're dealing with the infinity. So there is no fixed value of elements, or there is no fixed number of elements that you're going to subject. Meaning to say there is no boundaries. While dealing with your infinite population, you already know how many elements, no, are you going to subject, no, or you're going to subject in your research. So that's your finite and infinite population. So let's deal with the calculation of variance and standard deviation of sampling distribution. Here is the formula, no, in computing your variance and standard deviation, dealing with your finite population and infinite population. Now for the variance, now for your infinite population, your sigma square x is equal to sigma square, or your staff population standard deviation sigma, over your n, which is your sample size multiplied by bigger n minus n. That will be your population minus your sample over your population minus 1. So that will be the formula for your variance dealing with your finite population. While in your infinite population, you're dealing with your sigma square x, or simply your variance, no, is equal to your sigma, or your population, or your variance for your population sigma over your n, which is your sample size, no, again, your sigma squared x is your variance from your sample, and your sigma squared, that will be your variance from your population. Now, dealing with your standard deviation, so we just simply take the square root of this formula, no, in your variance, so that will be equal to your standard deviation. Now, for the formula for your standard deviation under your finite population, that will be sigma x, or your standard deviation for your sample, is equal to your standard deviation from your population over your sample size n multiplied by square root of n minus n all over your n minus 1. So that will be your standard deviation formula for finite population. While dealing with your infinite population, your sigma of x is equal to sigma all over your square root of n, or your sample size. So that will be your formula, no, dealing with the standard deviation for your infinite population. So let us remember, the finite population correction factor can be calculated using your square root of n minus n all over your n minus 1, or simply the square root of your population minus your sample all over your population minus 1. So the finite population corrector factor is used when your sample, no? When your sample without replacement from more than 5% of the population. So we simply use the finite population correction factor, no, when your sample is without replacement from more than 5% of the population. So if there is no replacement, so the CLT, or the central limit theorem, does not hold and the standard error, of the estimate will be too big. So we simply use your CLT, no, if your n is greater than or equal to 30. So we only apply your CLT if your n is greater than or equal to 30. So for example number 1, so what is the mean of the population if the mean of the sampling distribution of the mean is 5.2? So steps, no, there are two steps here. First is to identify the given information. So there is a given value in your problem that your sample, or the sampling distribution of the means, or your mu x is equal to 5.2. When you say, so find the mean of the population mu. No, since based on the observations, no, that we get from your histogram on our previous slide, no, that your population mean is equal to your sample mean. So meaning to say, if there's a given value of the mean of the sampling distribution, which is your mu x, so that will be equal to your population mean also, which is your mu. So since your mu is equal to your mu x, therefore we can say that your mu is equal to your 5.2, or simply your population mean is equal to 5.2, because we hold this statement or observations from our previous slide that your population mean is equal to your sample mean, no, from the histogram that we get in the experiment of rolling a die. So based on our observations from that histogram, no, so we simply conclude that your population mean is equal to your sample mean. That's why we adopt your 5.2 as a value also of your population mean in this example number 1. For example number 2, the weight of athletes is normally distributed with mean of 65 kg, and the standard deviation is 2 kg. If 50 samples, no, consisting of 16 athletes, each are drawn from the finite population, what is the mean and the standard deviation of the sampling distribution of the means? Why there is a finite population dito? Because there is being mentioned here that we only subject 16 no, from the 50 samples. Now, in your first step, you need to identify the given information. So there's a given value. Your population mean is equal to 60. Your standard deviation from that population is equal to 3. Then your n is equal to 16 because we only subject your 16, no? So your sample size is equal to 16 from the 50 samples because we only subject your 16 here. So you need to replace these two here, so that will be equal to 3. So it's a typographical error, no? No, your standard deviation from your population is equal to 3. So from your step number 2, find the means of the sampling distribution. So based again from our observation from our previous slide, no, using your histogram, your mu x is equal to your mu. That's why we can say that your mu x is equal to your mu, or simply your mu x or your sample mean is equal to 65, because there is a given value of your population mean here. Now this will be your sample mean. Now for the third step, find the standard deviation of the sampling distribution. So since the formula in infinite, so we use the formula. So there is a given formula for this infinite when you are asked to find the value per variance and your standard deviation. So since there is a given value of your population standard deviation and the sample size, so we simply substitute the given values for your population standard deviation and your sample size to the given formula. So that will be 3 over your square root of 16. So since 16 is a perfect square, so if we take the square root of this 16, so that will be equal to 4. So our standard deviation for our sample, no, which is 3 over 4. So if we convert this 3 over 4 to decimal, so that will be equal to 0.5. So meaning to say the standard deviation of the sampling distribution is equal to 0.75. For example number 3, what is the population standard deviation? So we're asked to find the value of your population standard deviation if the variance of the population is 25. Now identify the given information. So here there's a square here because we're dealing with the variance. So the given value is the variance of the population, which is your sigma square is equal to 25. Now, what we need to do now is to take the square root of this one for us to find the value of the population standard deviation, no? Which is your sigma x, no? Or simply your sigma, since your standard deviation, no? So find the standard deviation of the population Q, or sigma x, no? So the standard deviation is can be obtained by getting the square root of the variance of the population. So there is a given formula here, which is your sigma x is equal to square root of your sigma, no? So we just simply take the square root of this 25. So since 25 is a perfect square, so if we take the square root of 25, so that will be equal to 5. So meaning to say the value of your standard deviation of the population sigma x is equal to 5. Now our final answer will be equal to, for example number 4, so find the finite population correction factor. N is equal to 270, which is your population, no? So this will be the value of your population, and this will be the value of your sample, which is your smaller n. So given here is the sample and your population value, which is 270 and 47. Now, the formula for finite population correction factor, no, that will be equal to square root of n minus n, or population minus sample all over your sample minus 1. So if we take the square root of this resulting value, so that will be your finite population correction factor. So we just simply substitute the given values to your given formula, which is your 270 and 47. So that will be square root of 270 minus 47 over 47 minus 1. So the resulting value from this one is equal to square root of 223 minus 46. So if we, in computing this kind of radicals, no, we just simply input, no, direct we directly input this one to your calculator, and we can get the value of 2.2018. So how we can solve with this radical, no, or how we can deal with this radical? So by simply or we directly input, no, this radical sign and the fraction, no, inside your radical, then our resulting value is 2.2018. So our final answer is 2.2018. So our finite population correction factor is equal to 2.2018. So for example number 5, find the mean mu, or your population mean. So the variance sigma square and the standard deviation. So these three values are from your population. Of the population given when your sample size is equal to 25, your sample mean is equal to 20, and your variance from your sample is 2.3. So the sample size n were randomly selected from the population. So first step, you need to know your given values. So that will be 25, 20, and 2.3 as a value for sample mean, and your variance from your sample. Now, we can adapt again, no, the concept of your population mean, which is equal to your sample mean. That's why your population mean now is equal to 20. Now, in computing for the variance, no, for your population, we simply use this formula, no, your sigma or your variance from your sample is equal to your variance from your population square is all over your n, which is your sample size. So we just simply substitute and we cross multiply this 2.3, no, 2.3 multiplied by 25, that will be equal to sigma square or your variance from your population. Now your variance now is equal to 57.5. But again, we're not we're not only after to your mean and variance, but we're asked to find also, no, the value of your standard deviation. So by simply taking the square root of this 57.5, so that will be square root of sigma square, or the square root of your standard deviation from your population is equal to square root of 57.5. Now, the value for the standard deviation for your population will be equal to 7.5829. So our final answer will be equal to 20, 57.5, and 7.5829 as a value of your mean, your variance, and standard deviation of the population. So thanks for watching. If you want to like, comment, share, and subscribe, please do so. Again, I'm Arvin Enriquez, your subject teacher for probability and statistics.